Hey class, Mr. M here with a calculus lesson. Just a comment, this message may be interrupted from time to time because of announcements for people being dismissed, so hopefully those won't become too distracting. We shall see. Here's our agenda. We're going to do some review. We'll talk about the two new concepts called u-substitution, which is what you do when the reverse chain rule fails, and also a process called finding C, which gets us a particular solution rather than a general solution to a differential equation or an indefinite interval. I'm going to go at kind of a fast pace here, so if it does go fast, of course you can watch the video a little bit slower or rewind, but hopefully this will allow us to squeeze in a lot of content. One thing I would like you to do, either now or maybe in class when I see you again, is to formalize the reverse chain rule. So in your booklets, if you have them, you may add these to your booklets. This will help you understand the concept of the chain rule in reverse. So if you have what we want, right, which is that the derivative of the inside part is indeed sitting right next to it as part of your integrand, that means you can just focus on the f prime part and take its antiderivative, which is just f. So if you get the reverse chain rule, then that's a lot of problems like these. Your assessment, which was planned for today, Friday, the 22nd, but will instead hopefully be on Monday, will deal with these concepts, basic antiderivatives. And I was going to spring these on you as a surprise. Hey, here's some review, but with so much missed time, it probably isn't fair. The assessment will also cover linear approximation and some simple related rates, not too complicated. And one problem of each for those two review concepts. Several basic antiderivatives then. So here's some review concepts. These are questions that you might expect to appear on the assessment. I'm not going to work through these because they're pretty straightforward, but here, just to give you a sort of a clue, you'll have to rewrite the first term in order to make it anti-differentiable. The second term may look scary, but it's really not. And of course, that one should be fairly simple. So simply take the antiderivative of each, right? And you should be okay. And then of course, don't forget plus c. So you should get here 3/7. Sorry. Well, I said I wasn't going to do it, so I won't do it. But you get the idea. These are the kind of questions you may expect. Be especially vigilant for the minus sign here, right? When you think about what your antiderivative would be. Okay, the second one is very, very simple, but I wanted to make sure you recognize the fact that your variable of integration is a little bit different. So this one I will work out. It's very simple. So the first one I didn't work out. I just kind of help you get started here. On the second example, right, if the derivative is 5, then the original function was 5x, right? But this is not an x problem. This is a theta problem. So it'd be 5 theta plus c. Simple as that. But the important distinction here is variable of integration. So questions like that you may expect on Monday. So what I planned for us to do is that after your assessment, you would then do some review problems dealing with the reverse chain rule, except in a trigonometric context, which makes things a little more complicated, which are these problems right here in your textbook, 301, numbers 33 through 35, and 39 through 40. So those look kind of like this. You'll have something like, let's say, 3x squared, and then this might be cosine of 4x to the third dx, right? So what you'll have to figure out then is, okay, here's the inside part. The derivative of that should be 12x squared. Well, that's not 12x squared, but if I cheat and make that 12x squared, well, I have to account for that. And then you can take the antiderivative of just the cosine part, which of course is sine. All right? So here are the solutions to those. I encourage you to pause the video, work on these problems as best you can, and then take a look at the solutions, which are right here. The second two are a little more complicated. If we have some time next week, we'll talk about those in some more detail. But basically what you want to look at them as is, I think in 39, for example, you have something like cosine of 2x and sine of 2x. What you want to think of that is as if it's a polynomial raised to the first power, right? So you have kind of the derivative of the inside part here. What you need is a 2 and a 1/2, right? And then you have exactly what you need, so you can smile. So those are a little bit harder. The first three you should be able to get. They're pretty straightforward. All right, on to some actual content now, and that is u-substitution. Now, a comment here before we get started. U-substitution does not appear very frequently on the AP test. Sometimes it does, but some people do prefer it to the reverse chain rule. But typically, you use it when the reverse chain rule fails. It can be used in place of the reverse chain rule, but typically it's used when you can't use that rule. So it's actually more powerful, but because it's more confusing, I don't like to encourage it for all problems, but only when you have to. So let's examine a problem like this. The integral of 2x cubed times the cube root of x squared plus 1 dx. All right, so you approach this problem the way you normally would. Maybe rewrite this so it's a little more digestible. And then you check to see, okay, do I have the inside part the way that I want it to be? Let's see, the derivative of the inside part is 2x, and that's not what I have out here. I have 2x cubed. And I can't cheat because I would have to change the exponent, right? 2x cubed would have to somehow go down to just plain old 2x, and that's not going to happen very easily. It's not just a coefficient difference. So we cannot use our same strategy, right? So we're sort of not smiling here. It's not good. We can't use u-substitution. Sorry, we can't use reverse chain rule. So we have to use the u-substitution method. And the way you do that is you make an assumption, right? You say, let's take the inside part here that's given us all this problem, and let's call it x squared plus 1. Let u equal x squared plus 1. So that means our problem is going to look now like this. 2x cubed times all this junk raised to the 1/2 power, oops, got ahead of myself, dx. Except now, the inside part is simply called u. All right, now this may look a little complicated because we have a u, but we also have all these x terms, right? It's dx, we're integrating with respect to x, and yet we have this u term. And that is complicated. So we'll have to change, ultimately, all of these things to take it away from being an x problem where it was unsolvable into making it a u problem where hopefully it is solvable. And that's once again where this assumption is so powerful. Now this single assumption also has several, lesser assumptions which can be derived from that. In other words, if this red statement is true, then these following blue statements are also true. If we assume that u is equal to x squared plus 1, then it must follow that du dx is equal to 2x, right? If the red is true, if we take that for granted, then the blue must also be true. Now this part is a little unorthodox. We haven't seen this next step before, but it's called separation of variables, right? Remember, derivative is slope. Slope is rise over run, or change in y over change in x. So what I'm going to do is I'm going to temporarily separate the du and the dx. Normally we think of it as one quantity, and it typically is, but we're going to separate them in order to allow us to take out this original dx. Remember, we want to take it from an x problem into a u problem. So we need to replace dx, meaning we need to solve this equation here in blue for dx. That way we can substitute whatever we have remaining in place. So I'm going to multiply both sides by dx, right? You can also think of this as cross multiplication if you wanted to put this over 1. Same idea. And I'm going to divide both sides by 2x. And there we have a statement which is equivalent to dx, right? This dx right here. So we're taking an x problem as was given, unsolvable, and managing it so that it becomes a u problem, which again hopefully is solvable. And we're almost there. 2x cubed times the inner part, which we assume to be called u, just a variable, times no longer dx, but rather du over 2x. Because these things right here, according to what we did in blue over there, are interchangeable, right? That's what this step right here says. If we assume the red, then this blue stuff must also be true because we didn't break any rules. And now things start to look a little interesting. Let's consolidate this sum. We have 2x cubed u to the 1/2. I'm going to go ahead and bring the du down. But I'm going to take this over 2x part and just write it as 1 over 2x, because it's the same thing. Right? Dividing by 2x is the same as 1 over 2x. And the reason I do that is this will allow me to make some nice cancellations, right? 2 and 2, those cancel because they're multiplying and dividing. X cubed over x, well, that's just x squared. So all this business becomes x squared. I'm going to leave this red. Over, right? There we go. I said over, I meant 2 to the 1/2. So there we go. So in that last step, a lot of stuff happened. We replaced dx with this blue term here, and combined that with our sort of leading term, which was the part where the reverse chain rule failed, and we sort of cleaned it up a little bit so that the 2's were gone, and now x cubed, importantly, has now been brought down to x squared, right? We brought it down a power. And if you notice, we're almost at a u problem, right? This matches, but we still have this pesky x squared. And that's sort of like a thorn in our side, right? We can't get rid of it. It's still there. Aha. Let's go back to our original assumption, right? This is the granddaddy of them all. This is what allowed the rest of it to be true. Let u equal x squared plus 1. Well, that is equivalent to saying, right? It's equivalent to saying u minus 1 is the same as x squared, right? It's just solving for x squared. If the red is true, then all the blue stuff we came up with, that was one of our, sort of things that follow. It's one of our sub-clauses that come from the original. And so is this green one. This green one also must follow if you accept the red one. If you accept the red, then the blue and the green are sort of like the fine print. These also have to apply. And here's what's so important. X squared is equal to u minus 1. That's equivalent to the original assumption. Well, I can now take out x squared, can't I? No longer is it x squared. X squared is equivalent to, as we just saw, u minus 1. And that's going to multiply by, I'm going to get rid of the parentheses here because it's just a single u raised to the 1/2 du. Okay? It's a very long problem, but it can become that way. We don't have too many u substitution problems to work on, just a few. Okay, so there we have it. And now, what's useful is we can now distribute, right? Because there's nothing, the green parentheses there is not being raised to anything. It's just u minus 1 times this u to the 1/2. So that becomes, I'll do this in a new color because we're sort of combining terms, u to the 3/2, right? Minus u to the 1/2 du. An x problem originally, all the way many eons ago, right? This original x problem has been, transformed somewhat mysteriously into whatever the heck u is. We know what u is, that was our original assumption. But the good thing is we can now take the antiderivative of this. U to the 3/2 used to be u to the 5/2, right? Dividing by 5/2, which makes it 2/5, minus u to the 1/2 used to be u to the 3/2 times 2/3, plus, of course, as ever, c. Which, that's fine. Sure, you can accept that if you want to, but let's not forget our original assumption, the key to all of this, let u equal x squared minus, that was a plus 1, I believe. That was plus 1. That u equals x squared plus 1, which means they gave us an x problem, we turned it into u in order to make it a little more solvable, but now let's turn it back to the way it was. 2/5 x squared plus 1 to the 5/2 plus 2/3 x squared plus 1 to the 3/2 plus c. So all I did there was I replaced the u back with what it was. We replaced x squared plus 1 with u, and now we did it back again at the very end of our problem. So you kind of see a nice symmetry here in this problem. That's a lot of work. I'm not going to lie. It's a lot of work. And the reason it's so hard is the reverse chain rule fails. We don't have that nice, convenient recognition of saying, oh, okay, these are the same, so this derivative was the derivative of the inside, and you can tuck it all back in. Well, no, that doesn't work here. So you have to use this method called u-substitution. So that's kind of a hard one. Take a look at that, maybe pause the video, walk through the steps, and justify them for yourself before moving on. All right, on to our next concept then. And I'll put some more video links in the Weebly site so that you can look at these in more detail for u-substitution. The next concept, or final concept, is called finding C. In other words, getting an actual C value, a number, rather than leaving it sort of undone and generalized. So I want you to think about the answer to this question. What is the solution to an indefinite integral? In other words, if I give you a problem like the integral of something is equal to what, right? Or dx, I should say. Dx is equal to what? What is the answer to that? What is the solution to an indefinite integral? If you've thought about it, you know that the answer is not just a single function, right? Not just a single curve on a graph, but a family of curves, all of which differ by this term c. So for example, if our original function is something like 2x, right, which looks like this, if that's f prime, then we work backwards to figure out not just a single function that has 2x as its derivative. For example, this parabola, x squared, has 2x as its derivative, but so does this parabola, also has 2x as its derivative, and so do all parabolas which are vertical translations of x squared, right? So the answer to this, what is the solution to an indefinite integral? The answer is a family of functions, not just x squared, but all of its pesky, annoying relatives too. And this is kind of what that looks like, right? You have all of these curves, all of which have the same slope. For example, and I made this picture, I edited it on my own, so it may not be perfect, but for example, at this x value here, you have a slope, and here has the same slope, and the same slope, and the same slope, right? Those are supposed to be vertical of each other. It didn't quite work out that way, but you get the idea, right? At a certain point, x, no matter what c is, whether it's translated up or down, all of their derivatives are the same. All their slopes are the same. Or they would have parallel tangent lines, right, to connect it back to algebraic geometry, right? Parallel tangent lines. So the question is, how do you pinpoint a particular solution? How do you find which one of those curves is the one that you are actually working with in a particular situation? Well, in order to do that, you would need a particular point. Right? You need a specific single point to say, okay, I want a curve that goes through, that has this slope, right? Which all of these do, but I not only want that, I also want the one that happens to go through this dot. And that says, okay, from this big list, I can just choose this one function, because this is the only one, right, that also goes through that dot and has the additional condition of fitting the derivative that you have. So having that single point allows you to take away all those family members and just single out the one that you want, which is the one that matches that curve. Okay? So here's an example problem. Problem reads, a car's acceleration after time t equals 0 can be modeled by the linear function a of t equals 4t plus 2 meters per second squared. Find its position function. All right, so a lot of stuff going on there. We have to think about the hierarchy, right? You have position, its derivative, which is a rate of change, is velocity, and its derivative there is acceleration. And what we're given is acceleration, and we have to work backwards up to position. So think about how many steps that's going to take, how many antiderivatives that will involve, okay? So let's start with the outset. A of t is equal to 4t plus 2. Well, if I want the velocity function, which is, again, one step higher on this hierarchy, if I want the velocity function, I need to take its antiderivative, right? I need to go backwards from the acceleration. And the antiderivative, of course, is the backwards derivative, right? So the integral of my velocity function is the integral of 4t plus 2 dt. And that's pretty easy, isn't it? Let's try to color code this the best I can, but maybe a few additional effort. V of t is going to equal, let's see, 2t squared plus 2t plus c. 2t plus c. Okay. Double check before we move on. Derivative here is 4t, derivative here is 2, derivative c is 0. Okay, we're done. Well, that's not a very satisfying velocity function, is it? Because this plus c means you have all sorts of velocity functions. 2t squared plus 2t plus 5, 2t squared plus 2t plus 7, and gazillion others. So how do you single out which velocity function is actually ours? We need some more information, don't we? So in problems like as you'll have in your homework, you'll be given this additional information in the original problem, which tells us that at a specific moment, right, at velocity at time t equals 1, the velocity is 6. So how does that help us, knowing that? That's equivalent, right, to this point on the graph, 1, 6, on the velocity graph. So now we can use that information to figure out what c is, because that's our only variable left. Right, v of 1, right, the velocity is going to equal 6, and v of t, right, has become v of 1, which means our t value is 1, 6, t comma v is our point there. So that's going to become 1 squared plus 2 times 1 plus c, right? T equals 1, the velocity v equals 6, replace those, and there you go. Well, this is a very easy equation, isn't it? 6 is equal to, that's just 2, plus 2 plus c, 6 equals 4 plus c, which implies that c equals 2. Finding c, well, we found it. Awesome. Which means our velocity function, which was this thing right here, right, can now be refined to become more specific. Change this a bit. Can now be refined to become more specific. No longer is it this generalized plus c, right? Our true v of t, our actual velocity function, is the following: 2t squared plus 2t, not plus c, but since we're given this additional information, this implies that our c value here must just be plain old 2. So now we found our velocity function. Well, we were asked for position, weren't we? Well, going back to our hierarchy, right? We're here now, we need to go up one more step. Well, in this direction we take the derivative, and in this direction we take the integral, right? To go backwards, the antiderivative. Okay, so how do we do that? The antiderivative, I've lost the color scheme here, but I think we'll manage. Choose purple. The antiderivative of velocity is going to give us position, which mathematicians typically call s of t. I'm not really sure why, but I'll stick to that notation. This should be dt. All right, so I need to take the antiderivative of the thing we just found. Okay, well, antiderivative of 2t squared plus 2t plus 2 dt. That shouldn't be too bad. I'm sorry the t's and the pluses match each other so much, but what are you going to do? All right, so this will be 2/3 t cubed, right, plus t squared plus 2t plus c. Right, that should be our position function, the antiderivative of the velocity function. Because the velocity is the derivative of the position function. Let's make sure I did that right. 2, right, okay. 3 cubed, yeah. 2t plus 2. Okay, well, we still have this plus c. How are we going to get rid of that? Well, we need some more information, don't we? And that's where this thing comes into play. Additional information is, so at this particular time, at 3 seconds, I believe it was seconds, our position is 35 meters, meaning after 3 seconds ticking along, our car is 35 meters from its starting point or on the track or what have you, right? 35 meters along. Okay, well, that's going to help us, isn't it? As you can probably see. S of 3 is the output. Let me write this in function point notation so you can kind of see it. Right, 3 comma 35. We need where this curve passes through that. Okay, well, 35 is our output. It's going to equal 2/3 3 cubed plus 3 squared plus 2 times 3 plus c. Okay, just replacing t with 3 and s of t with 35, our position and our time. Okay, well, that shouldn't be too bad. 35 equals 2/3 times 27 plus 9 plus 6 plus c. 2/3 of 27 is 18. So 35 equals 18 plus 9 plus 6 plus c. 18 plus 9 is 27, right? Plus 6 is 33, right? Subtract 33 from both sides. So at this point, what we have is 35 equals 33 plus c. Subtract 33 from both sides. And you have 2 equals c, once again. All right, a lot of work. We're almost there. That means our position function has been refined into the following. 2/3 t cubed, right, plus t squared, plus 2t, plus not c, but just plain old 2. We're asked for the position function, and there it is. So, notice what we needed here, right? We needed additional information. We needed, hey, what was the velocity at a specific moment? Well, at 1 it was 6. And what was the position at a specific moment? Well, at 3 it was 35. And that allowed us to find the value of c. In this case, twice, because we had to take 2 antiderivatives. Oh, that's a last slide. Okay. Well, there you have it. U-substitution, finding c. A lot of work, but soak it in, look it over, and see how you do. Okay, I went ahead and added the last slide. I'm not going to assign these now. I'm going to expect these to be done at a later date. But if you wanted to go ahead and get a start on these, if you have a lot of stuff coming up, you're welcome to do so in this time, now that you have an idea of what U-substitution is and what finding C requires. If you want to work on these, great. If you don't want to, you can wait till later, because I won't expect it done on Monday. I'll expect it done at a later date, which I'll announce on Monday. All right, so just to review, once again, right, these concepts can be a little challenging, but I encourage you to go back to the video. But more immediately, right, you have your assessment coming up on basic antiderivatives, linear approximation, and related rates. So thanks for watching. Stay safe during the weather, and I'll see you hopefully on Monday.